Chapter 3 deals with mass relationships, chemical reactions, stoichiometry, and a term called the mole. All right, I just want to point out a couple things here. To find the weight of a compound is going to be important. You need to use the periodic table, okay, and look up the masses on the periodic table of each individual element. Okay, so sodium chloride, you look up sodium, it's 22.99. Now, when I'm doing this in class on the board here or whatever, I round to 23. It's not really going to throw things off that much. And depending on the periodic table you pick up, so I'm not going to be a stickler for that. Chlorine's 35.5. So again, it's about 58.5 for sodium chloride. If I have little subscripts here, based on how I'm bonding, I have to multiply the weight by said subscripts. Okay, so sucrose would be 12 times 12 for carbon, 22 times 1 for hydrogen, and 11 times 16 for oxygen, and then you add them up, and that is the total mass of the compound. Now, a couple things I want to show you here is what if I do have one of those polyatomics. That's the first thing. I got a big long microphone cord here and I don't want to roll over it. But let's say I do have a polyatomic. All right. And let me think of one. All right. So calcium nitrate. And I wanted to find the mass of calcium nitrate. Okay. So calcium, if I look it up, is 40. All right. Nitrogen is 14 and oxygen is 16. All right. If I look them up. So I've got calcium. I've got one of them. I multiply it by 40. I've got 40. Okay. I've got nitrogen. Nitrogen, I have two of them because I've got to distribute the parentheses. Okay, so 2 times 1 is 2. I have 2 times 14. That's 28. And then 3 times 2, I've got 6 oxygen at 16 apiece, which is 96. So if I were to add this all together, 160 minus 4, 164 would be the mass of calcium nitrate. Okay? So 164 would be the mass of calcium nitrate. Let's just imagine also, all right, and I'm just going to make something up here, but let's imagine it's a hydrated salt, all right, which I talked about in that separate video. So it would say like times, let's say 3 waters, and where students get confused, so we just did the math on this, and we said this is 164. Now, I have 3 waters. Now, I could break this down and say, okay, hydrogen, now this 3 out front gets distributed, 6 times 1 roughly, and then oxygen is 3 times 16. So I have 48, and I have 6, and I have 54. Now, the total mass of this, which would be, if it existed, calcium nitrate trihydrate, would be add these together. All right, so 8, 1, 218. Students see this multiplication and multiply it. The multiplication is just a way of writing out the name of a hydrated salt. Do not multiply it. I usually treat the water by itself and then the compound by itself and add them together. And honestly, you use this so often, water is always 18, so it's 18 times 3. But if you feel like you have to break it down, then do so. Now, what we could do with the mass is figure out the percentage of each compound. We did this in the last one, but just to reiterate it, if I wanted to know how much, let's just do oxygen. How much oxygen is in this compound up here? Well, I know the total is, what did we say, 218, right? So the total is 218. If I want to know how much oxygen, what's the percent oxygen, or let's say what's the ratio of oxygen, and then we'll figure out what's the percentage. I would take the total part over the total. The total is 218, and now I got to figure out each oxygen. So I've got 6 oxygen here and 3 there for 9 total. Okay, so 48 and 96, which is 142. No, that's wrong. 144. So it'd be 144 over 218 would be the ratio. And if I wanted to find the percentage, I would take that and multiply it by 100. Okay, and that's known as finding, the parts by mass of each individual component. And if you find all the parts by mass or all the ratios, they should add up to 1. If you find all the percentages, to double check your answer. So I'd have 4 different parts: calcium, nitrogen, okay, oxygen, and hydrogen. All right. So there's that. Now I can also break it down and do it as, what if I wanted to know how much nitrates are in there? Okay, I could break it down as a full polyatomic, just so you know that. Okay, and I could, figure out, all right, so again, our total was 218. All right, and then I want to know nitrate. So if I break nitrate down, nitrate is 14 for the nitrogen, plus 3 times 16 for the oxygen. All right, and I have 2 of them, so I'm going to have to, these parentheses are wrong. I got too many parentheses going on here. Let's do that. That works. Okay, and then I have 2 of them based on this little subscript, so I'd have to multiply that out like that. So 14 plus 48 is 62. Then 62 times 2 is 124. And then I would take the 124 over the 218. Okay. If I want to know parts water, you could break this down multiple ways. It doesn't have to be parts of an individual element. It could be a polyatomic. It could be the water. All right. Any questions on that? So when erase this, perfect. Okay. New erasers, new markers. I'm all excited. Doesn't take much when you get to be my age. There were the new erasers and new markers. And Amazon Prime is my devil during quarantine here. But let's talk about another term. We're going to talk about a term now that deals with the mass of something, and it's known as the mole. And what the mole was basically studying is how many, let's do the number of carbon-12 atoms in 12 grams of carbon-12. Okay. That's what the mole essentially measured. All right. What they found is that there are 6.022 times 10 to the 23rd atoms of carbon-12 in 12 grams of carbon-12. Okay. This is known as Avogadro's number. And the thing about this is, what they discover, is that this value is equivalent to what they call 1 mole. So 1 mole of carbon-12 contains 12 grams of carbon and 6.022 times 10 to the 23rd atoms of carbon. Okay? Now, that being said, the term a mole is like the term a dozen or a gross or whatever. If I say I have a mole of something, it doesn't matter. A mole of carbon, a mole of sodium, a mole of tape. I'm making stuff up, of course. But if I say I have a mole of something, if I said I have a dozen apples or a dozen cars or a dozen people or a dozen kangaroos or a dozen pieces of garbage, every time I say dozen, you're picturing, you just pictured in your head 12 people, 12 kangaroos, 12 cars, 12 pieces of trash. Well, the mole is the same thing. If I say I have a mole of something, I have this many atoms or ions or molecules, what your book calls formula units, okay, of that substance. And the thing is, they're all equivalent to each other. I have the same number. Now, the difference is if I said to you, okay, what's the difference between a ton of bricks and a ton of feathers? You're going to say, well, they're both a ton, so neither weighs more, so they're equivalent. Okay, but what's the difference between the two? Well, it's going to take a lot more feathers to reach a ton than it is bricks. That's the same thing with a mole. How many grams are going to make up a mole of sodium is different than how many grams of carbon-12 are going to make up a mole of carbon-12. Okay. So, now I just want to point out Avogadro's number. We're going to talk about Avogadro. Avogadro, now listen to this. Now you think your life is boring and not exciting and whatever. Avogadro was a lawyer whose hobby was to study physics and chemistry. So imagine that your life is that exciting, that you're in law, but you, as your hobby, do what we're learning today. Sounds exciting. Avogadro didn't find Avogadro's number. A French chemist found Avogadro's number, admired Avogadro, named it after Avogadro because Avogadro was laying stuff down for this. Okay, just to point that out in case you're ever on Jeopardy. But here's the deal with a mole. Okay, so I want to know the grams. I know I have 1 mole of the substance. And I know that always equals Avogadro's number. Okay, of formula units. The old book used to put FU on here. They used to put F.U. Yeah. We're not going to do that. Not formal unity here. Formula units. Although formal unity would be nice too. All right, formula, I did it again, units. Something's telling me to do unity today. All right. So how do I know the grams? Well, the grams is the mass of said substance. Okay? So if I look up sodium, for instance, on the periodic table, sodium is 23 grams. 23 grams is equivalent to 1 mole of sodium, which is equivalent to 6.022 times 10 to the 23rd atoms of sodium. We looked at water, right? I said water is 18 grams. 18 grams of water is 1 mole of water, which is equivalent to 23 molecules of water. Okay, hydrogen is 1. Let's imagine it's a hydrogen ion. Hydrogen is 1 gram. That would be 1 mole of hydrogen ion, which is equal to 6.022 times 10 to the 23rd ions of H+. Okay? So the mass of my substance is equal to 1 mole. So if I had 46 grams of sodium, I'd have 2 moles. And I'd have 2 times Avogadro's number. If I had 36, or 54, with our 3 H2Os, 54, I'd have 3 moles of water, or 3 times Avogadro's number. Now, questions on that? Again, if you don't have questions, you could just type no for me so it relaxes my anxiety. If you guys think you have anxiety over the course, I feel like if you guys fail, I fail, even though it's all on you, but I take it personally. Even though they told us never take it personally, I do. All good? Okay, cool. Brittany, you are my litmus test, really, just so you know. I don't mean to point you out, but you really are my litmus test because you were the one, like, the most nervous coming in. So if you're saying no, I'm confident then. Not to pick on you. And not to lessen any of the other ones. If you do have questions, let me know. All right. Okay. So, I need you to write this down or mark down in the video at about 15:55. He's going to give us gold. All right. You can't compare grams to grams. Okay? I can't look at this and say, okay, I have 30 grams of O2, and I have let's say 20 grams of hydrogen, of H2. Let's do that. And I say to you, which one do I have more of? Okay, and you would say, well, you have 30 grams of O2, so you have more of that. The thing is, you can't compare grams to grams because grams are different things, and there is no equivalency factor there. What you can compare, though, is moles to moles. And if you go back to chapter 1 when we were talking about things and it said amount on the metric system, okay, it was right under current is in amps and then amount is moles. And I said, we'll talk about that in the future. Welcome to the future. When we're talking amount in chemistry and which is more, we're not looking at grams. You can't look at the grams. You have to look at the mole ratios and the mole relationships. You can compare moles to moles. Okay? Which means, and here we go, and this is why I took my time with conversion factors, gave you homework, talked about them and everything. If I want to compare 30 grams of oxygen to 20 grams of hydrogen and see which is more, then I've got to convert my grams of oxygen to moles of O2 and my 20 grams of hydrogen to moles of H2. All right. It's a terrible looking arrow. But that's what I have to do. I can't look at grams of something and grams of something else. All right. And compare them. I have to compare moles. So if there's one thing you take away from today, it's this up here. I can't compare grams to grams. So here's what we're going to do. All right. I'm going to write it up here so we can keep it for the rest of the lecture. We're going to draw our factor label method boxes. But we're going to use this specifically for moles, and here is your map, Dora and Diego. All right, here we go. In this first block, we'll go what I know, or what I'm given, and I should copyright this because this is my thing. So we'll copyright it, we'll trademark it. All right, what I know in grams goes on the first block. In our next block goes something called the molar mass, with grams on the bottom and 1 mole on top. Now you might ask, what is the molar mass? Well, go back to what we did. Sodium is 23 grams. That's equivalent to 1 mole. The molar mass is written as 23 grams per mole. So the value on the periodic table is how many grams per mole. Molar, mole, mass, mass, molar mass. Okay, so that's that. Next comes something called the mole ratio, and we'll break that mole ratio down when we do our example after this. So mole ratio, and on the bottom will be moles of what I know. Up here is the moles of what I want. Down here and last is the molar mass. Of what I want. One mole on the bottom always, and the respective grams on top. And if you could follow this map, there's not a problem that you will get wrong as long as you understand how this map works. Okay? So let's do a simple one to start. Let's say I've got 120 grams of sodium hydroxide, and I want to know how many moles of sodium hydroxide that is. Yeah, Brittany, you can round up just because, I mean, if you want to use the 22.99, go right ahead. It all depends on the periodic table you pick up, but just for me doing the math in my head here and doing the problems, it's just easier for me to round them up. If you want to be exact, then go for it. So I want to know how many moles of sodium hydroxide. So I look at my map and what I know in grams. Well, they gave me grams to start. Okay, so I'm going to put what I know in grams up top first, 120 grams of sodium hydroxide. And I really should write the words first and then put my line in like that. Okay, so 120 grams of sodium hydroxide. Now to get it to moles, I need the molar mass. I need the molar mass of sodium hydroxide, so let's break it down. Sodium is 23. Oxygen is 16 and hydrogen is 1. So 23 and 16 is 39 and 1 is 40. So the molar mass of sodium hydroxide is 40 grams per mole. So if I look at this, the grams go on the bottom to cancel out, 40 grams per mole. Okay, and then 1 mole on top. Now I suggest you write it out completely. Sodium hydroxide, sodium hydroxide. Okay, and then we cancel out. Grams cancel out, grams cancel out. It's just like doing factor label method. The only difference is instead of looking up a conversion factor like how many inches are in centimeters, you get to calculate the conversion factor. Here it is. 120 divided by 40 is 3.00 moles of sodium hydroxide. Okay. Now what if it didn't ask that? What if it asked, instead of the moles of sodium hydroxide, all right, let's do a different one here. What if it gave you, let's do water. What if it said we had 54 grams of H2O, okay, and I want to know how many moles of hydrogen that is. Okay, I can't compare grams of something to moles of something else. So I always, when in doubt, let's just put it that way. If they ask me grams and they want to know moles of something or grams of something else, I have to at least know to convert this to moles, because that is my junction. That is the way I'm going to connect everything. Everything runs through the mole. Okay? Everything runs through the mole. So I got 54 grams of water. I want to know how many moles of hydrogen that is. Okay. So here's what we do. Start with what we know. 54 grams of water. Look at our map. Our map says use the molar mass of, and if we want to, we'll put the molar mass of what we know. We'll put that right here. Okay. Molar mass, and my OCD is not going to allow that to happen because that's red and we wrote in blue. And I know that's silly, but that's the way my mind works. So I need to write it in blue, or I would be freaking out the rest of the lecture. If you're in the same camp as me, raise your hand there. If that written in red just drove you crazy. All right, 54 grams of water. Our first thing is to convert it to moles. All right, if you add up water, again, 16 plus 1, that's 18 grams of water. 18 grams of water is 1 mole of water. All right, grams and grams cancel out. All right, now, I'm in moles of water. I want to get to moles of hydrogen. I need to use my mole ratio. Now, here's where our mole ratio comes from. 40, I added, yes, as Anish just said there, I added the 23 for sodium. Yep, exactly. Okay, and the 18 for water here is coming from the hydrogen and the oxygen. Each hydrogen is 1 times 2, and oxygen is 16. So that's where the 18 came from. Now, my mole ratio, okay? 1 mole of a substance has the subscript moles as its ratio. So 1 mole of water has 2 moles of hydrogen and 1 mole of oxygen. Okay, if we look at another one over here, let's do C6H12O6, okay, which is glucose. 1 mole of glucose has 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen. So in our case here, we'd go right to here, and we would say mole ratio. For every 1 mole of water, there are 2 moles of hydrogen. And we would do the math. 54 divided by 18, which is 3 times 2, there should be 6 moles of hydrogen. Okay. What if I wanted to know moles of oxygen? What would I have to change up here if I wanted to know moles of oxygen? What would change up here if I wanted to know moles of oxygen? Yep, the mole ratio. And specifically, the only thing I'd really have to change is what? This would just change to 1 mole of oxygen, right? That's the only thing that would change, and we would be left with 3 moles of oxygen. So here's the thing, guys. Once you get this down, it's repeat, repeat, repeat. If you watch Family Guy, volcano insurance, volcano insurance, volcano insurance, over and over and over again. Does everybody understand where we get the mole ratio from? Because that's the big key that people get lost on. All right, let's use C6H12O6 as our example here. All right. I've got 90 grams of C6H12O6. I want to know how many grams of oxygen are there. Okay. So we would start 90 grams. We'll put a dot there so at least we have two sig figs, right? 90 grams of C6H12O6. Okay, I can't compare grams. I can't compare grams to grams. So I got to get to moles first. Okay, molar mass of C6H12O6. All right, let's break it down. Carbon is going to be 12 times 6. Hydrogen is going to be 12 times 1. Okay, or I'll do 1 times 12 since I'll stay consistent there. 1 is the mass times 12 of them. Oxygen is going to be 6 times 16. Okay, so we're going to do 12 times 6, which is 72, plus 12 plus 96. And it comes out to be the mass of C6H12O6 should be 180. Okay. So we'll put 180 grams of C6H12O6 on the bottom. 1 mole of C6H12O6 on top. Grams cancel out. Next is my mole ratio. What is my mole ratio of glucose to oxygen? What is my mole ratio of glucose to oxygen? Yep, 6-1. Vaughn, you got it. 6-1. So for every one of these big molecules, I have 6 oxygen. Okay, that's where that comes from. So for every 1 mole of C6H12O6, I have 6 moles of oxygen. Then I want grams, 1 mole of oxygen, and I look up the grams on the periodic table is 16 grams of oxygen. Moles cancel out, these moles cancel out, and now we do the math. Let's see, 91.5, 3, I don't even have to put in the calculator. 3 and 16 times 3 is 48. I believe it's 48 grams of oxygen. Okay. Now, what if instead of grams of oxygen, it asks for grams of hydrogen? All right? And here's the thing. This is why I'm doing it this way. I'm not going to rewrite it or anything because I'm going to show you that if you could do it once, you could do it 100 times. This would stay the same. 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 I would change this to my new ratio, 12. The subscripts tell me 12 moles of hydrogen. This would change to 1 mole of hydrogen. And this would change to 1 gram of hydrogen. Okay. And my answer would roughly be 6 grams of hydrogen. Now, the thing about our map and everything like that, okay, the thing about our map and everything like that is that you have to know where to start and where to stop. If they gave me moles to begin with, I just move forward, don't go backwards. If I'm going from one thing to something else. If they want moles, I stop here. If they want grams, I go all the way here. If they gave me grams and they want moles. So that's the thing. You have to understand where you are. If you're going from something to something else, never go, and they give you moles to begin with, never go back to grams. Grams is go step back, go forward. If they only want moles, stop here. If they want grams, go all the way. Okay? Questions? There's one little piece to add to the map, and I do want it to be a different color. It is if you want to know the formula units. If you want to know the formula units, you have to take an exit here. Okay, and what we need to do here is do 1 mole, and up here, Avogadro's number. And over here, 1 mole, and Avogadro's number. So if it said to you something like, you have trying to think of something that'll work. We did sodium hydroxide. I mean, anything will work. I'm just trying to do it for my math wise. All right, let's say we have calcium hydroxide. Okay. 40. Okay, yeah, that'll work. All right, so we have calcium hydroxide. And let's say, it doesn't matter. I have a calculator. We have 100 grams of calcium hydroxide. And I want to know how many molecules of calcium hydroxide do I have? Or ionic compounds, whatever you want. Now that's not moles. Molecules is, you see ions, molecules, atoms, formula units. Okay, you see any of those, you have to use Avogadro's number, but I have to get there first. Okay, so same principle. I have 100 grams of calcium hydroxide. Okay. Now, I need the mass of calcium hydroxide. So let's break it down. Calcium is 40. Oxygen is 16 times 2. Hydrogen is 1 times 2. So 40 plus 32 plus 2 is 74 grams of calcium hydroxide. That's 1 mole of calcium hydroxide. Now, that being said, Okay. I want to know how many molecules. So now, I don't want moles or something else. I want molecules. So I got to work my way up here. Okay. And say 1 mole of calcium hydroxide, 74 grams. 1 mole of calcium hydroxide has Avogadro's number of molecules. So I would take 100 divided by 74. Is 1.35 times Avogadro's number. And I'm getting 8.14 times 10 to the 23rd. Okay. If, let's do another one. They give you something like, we'll go back to water real quick. They give you water. They give you 54 grams of water. And they want to know how many hydrogen atoms are present. All right. Well, I know the first thing, I can't do anything with grams except get it to moles, so I'll do that. Water has a mass of 18 grams and 1 mole. Okay. For every 1 mole water, the ratio, so I'm right here in our map, the ratio is 2 moles of water because the subscript, or 2 moles of hydrogen because the subscript tells us. And now I want to know how many atoms. That's an Avogadro's number indicator. And then we do our math. And the answer will be whatever 6 times Avogadro's number is. 6 times 6.022 times equals 3.6 times 10 to the 24th. 3.6 times 10 to the 24th. Like so. And that would be atoms of hydrogen. All right. We can also start with the units and work backwards. Like if they said something like, hey, I have 3.07 times 10 to the 30th atoms of, or let's do ions, because we just did atoms. Let's do ions of sodium. And I want to know how many grams of sodium chloride do I have? Okay, so we work backwards. We're actually starting up here and coming back. All right, I have 30.07 times 10 to the 30th sodium ions. I need Avogadro's number to cancel out the ions. Okay. And that's equivalent to 1 mole. So 1 mole of sodium ions. I don't know why I wrote sodium. I wrote ions down here and just instead of doing this, Na+, which is a lot easier. So now we're here and we're going to work backwards. For every 1 mole of sodium ions, what's my ratio of sodium chloride? 1 to 1. Subscripts tell me. 1 mole of NaCl. And then 1 mole of NaCl has a mass of, now we're here, I got to use the molar mass to get to the grams. 1 mole of sodium chloride has a mass of 58.5 grams, roughly, of sodium chloride. Moles cancel out, and we do the math. 3.07 to the 30th divided by 6.022 exponent 23 equals that, times 58.5, and I get, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 3.0 times 10 to the, we could do 2.98 times 10 to the 8th, if I did my math right. Okay. So you can work both ways on the map to find whatever it is you're missing. Okay? Questions on this? There are practice problems. So review sheet 1. Okay, review sheet 1 on Blackboard for chapter 3. There's extra problems besides what I'm going to assign in the homework. Okay. But I have one more topic. And then, like I said, either late tonight or tomorrow at some point in time, I'll finish this chapter with stoichiometry. But I'm going to tell you this, and I'll tell you again at the end of the video. The balancing equations in stoichiometry is the same as doing this. The only difference is, where do I get my mole ratio from? I no longer look at the compound, but I'm just foreshadowing so that you don't freak out and say, oh my God, he's giving us new stuff. It is new, but it's the same thing, just applied differently. Okay. All right, so we have our map. Keep our map, love our map, learn our map. Okay. All right, the last thing I want to talk about today, and this actually puts us like about 75% of this chapter done. All right, is empirical formula. All right, empirical formula is the lowest mole ratio, all right, of a compound. All right. So what I mean by that is this. If I had hydrogen peroxide, which is H2O2, this is, as we've been talking about, the molecular formula. The empirical formula gives you the lowest ratio, which would be HO, because each one is divided by 2. Okay. So C6H12O6 that we just looked at, empirical formula would be CH2O. It gives us the lowest ratio possible. Okay. So, how do we figure out empirical formula based on data? Well, there's a couple ways, and it all depends on what you're given first. So we're going to do it the longest way, and then you just decide what you're given and where you jump in. Again, it's like a map again. but it's a process. Okay? Number one, you'll be given percentages. Okay? If you're given percentages of each element, all right, what we do, all right, is assume our sample is 100 grams. Even if they don't tell us that, they tell us our sample is 10 grams. We'll just assume it's 100 grams. Because the law of constant composition says if the percentage is 50% at 10 grams, it's 50% at 100 grams. And the reason you do this, the reason we assume 100 grams, our percentages become our grams. So if I tell you it's 50%, you assume it's 100 grams, then it's 50 grams. Just makes it that much easier. Number two, step two, convert your grams to moles. Step three, divide by the least moles. And step four is write your empirical formula. Okay? So let's do an example. I got to think of something real quick in my head here. All right. Yeah, let's do that. Okay, this will work. All right, let's do a problem and we'll follow these steps. Let's say we've got a compound that is 80% carbon, okay, and 20% hydrogen. And I want you to write out the empirical formula for this compound. All right, let's follow the steps. Step one, assume you have 100 grams so that the grams or the percentages become the grams. Okay, so I'm going to assume that. So I have 80 grams of carbon and 20 grams of hydrogen. Okay. Step two, convert your grams to moles. Okay, let's do that. 80 grams of carbon. Carbon has a mass of 12. 12 grams is 1 mole. Hydrogen is 20 grams of hydrogen. 1 gram per mole. Okay, so that tells us, all right, I'm going to come over here and write it, that I have 20 moles of hydrogen. And what is 80 divided by 12 here? 80 divided by 12 is 6.67. Okay, so that's the answers that I got from converting my grams to moles, step two. Step three, divide by your least number of moles. So between the two, which is the least? This one. So I'm going to divide by this. 6.67, divide 20 by 6.67. I get 1 mole of carbon. And 20 divided by 6.67 is going to be roughly 3. Yeah, 2.99. So, so this is step 3. Step 4, write your empirical formula. CH3. My moles tell me what my formula should be. Okay? So, now what if I was given moles to begin with? If you're given moles to begin with, you're already here. Divide by the least number of moles, write the empirical formula. What if I wasn't given percentage, I was given grams? Then you're on step 2 already. Write your grams, convert it to moles, then divide by the least number of moles, and write your empirical formula. Okay? Now, I do want to point out a couple things real quick. At 2.99 or like 1.01, it's okay to round. But let's imagine we did all our steps. Okay, where did I put my marker here? We do all our steps and we end up, okay, so this is going to be our step 3. We just divide it by our least ratio, and we got 2.5 moles of X and 3.0 moles of Z, and I want to write my empirical formula, what do? I have to double everything to get rid of that half. But if it's like 0.9, 0.8, something like that, you could round it up. But in real life, they're not going to work out that way. So really, our empirical formula would be X5Z6, because I would multiply everything by 2 to get rid of that. If it was 0.33, I'd have to multiply everything by 3, and so on. 0.25, multiply everything by 4. But if it's like 0.9, 0.8, 0.01, something like that, it's okay to round. Now, the issue with empirical formula is this. Okay? We just solved the problem with empirical formula, and we got a formula of CH3. Well, what's the molecular formula? Well, the molecular formula's possibilities are what? C2H6, C3H9, any ratio of this CH3, C4H12. Now, do these molecules exist? Not necessarily, but you see my point. It really doesn't narrow it down. So there's 2 more steps that are used, and we'll use these steps, and we'll say our empirical formula to convert it to a molecular formula. All right? In order to convert it to a molecular formula, you need to be given data. And the data you need to be given is, all right, what is my molecular weight? All right, molecular mass of the compound I'm looking for. So let's say we continue with the problem we did, and we have our empirical formula of CH3. And they tell us that the molecular mass of our compound is 30. And I want to find what the molecular formula is. So I want to find this based on the fact that I know my empirical formula and I know the molecular mass of the compound I'm looking for is 30. So here's what you do. Step 1, okay? Take your molecular mass, all right, also known as your molar mass. All right, take your molar mass and divide it by your empirical mass. All right, that's step 1. So I'm going to take 30, because that's my molecular mass, they told me. Divide it by my empirical mass. 12 plus 3 times 1. That's 15. I get a value of 2. Step 2, take your empirical formula and multiply it by your answer in number 1. I call it my X factor, but we'll say our answer in, my answer from number 1. So, in our case here, we take CH3 and multiply it by 2. And our molecular formula would then be C2H6. All right. So the first 4 steps get you to your empirical formula. The next 2 steps get you from your empirical formula to your molecular formula. All right. Any questions on what we did today? All right, cool. So let's do some homework. There's review sheets online. There's some problems in the slides that deal with empirical formulas and, sample problems and things like that in the slides and in the book. But if I'm looking at the back of the book, All right, we are going to start on page 135 here. And like I said now, I'm going to do a separate video on stoichiometry and things like that instead of crowding it in here that you could watch at your leisure. Come Thursday, or Wednesday, I should say, if you have any questions on Chapter 1 and 2 to review for Thursday's exam, let me know. Okay, we'll do that at the beginning of class or go over any of this homework. And then we'll start Chapter 4 because Chapter 3 will be done with the stoichiometry lecture that I'll be posting at some point in time. All right, so be checking back on that. You should get a notification if you ding that bell that I posted a new video. All right, 3.1 to 3.3 looks good. 3.1 to 3.3. All right, 136. Now, I know you guys are getting used to this book. You can see that they're grouped in multiple problems. So if you could do the one set and you're like, I'm good, I don't need to try the other, that's fine too. 3.8 to 3.23. That's all converting from grams to moles, moles to moles, things like that. Empirical formula stuff. So this is page 137. So page 136, page 135, page 137. 3.36 to 3.45. Sure. 3.36 to 3.45. All right. And that covers everything we did in lecture today. And my camera froze. I did write it down. The camera froze. This camera likes to freeze if the table gets bumped. So give me a second. I'm going to see if I can fix it real quick without stopping the live stream. But I might have to stop the live stream. But if you can hear my voice, it's page 135, 3.1 to 3.3. Page 136, 3.8 to 3.23. And page 137, 3.36 to 3.45. The good news is I can edit this video and sew it together if I can't get this to work. Give me 1 second. So the webcam might go black here while I dig in the back of the computer and unplug and replug it. The camera is so sensitive, it's dumb. Alright, I might have to restart the program. We'll see if we have the camera back. No, we do not have the camera back. Okay, I'm going to stop the stream and then come back, guys. Alright, guys, I'm back. So there's the homework. There is the homework. Pain in the butt. Yeah, I bumped this table that I use with my leg here, and yeah. But now there is the homework. Okay.